All right, so here are some of the things that we can be looking for, common patterns that appear in these sequences that we're dealing with. So the first thing are some factorials. We've seen it in a couple of them so far, 1, 2, 6, 24, 120. I see those kind of numbers. That must be in factorial. And then, of course, remember that this thing is going to continue beyond that. I sometimes have in alternating terms. We saw that, again, both of these on that last example. And choosing between an n and an n plus 1 here, it just depends on, is the first term the negative one or is it the second one that's negative? Sometimes we have even and odd, some kind of even and odd numbers, or maybe even and odd powers within our sequence. If that's the case, think about back in geometry and algebra or whatever what the algebraic definition of even and odd number is. So I can write that as an equation as 2 times n whenever it's even. And if I want odd, I just add or subtract the number 1 from that. So I'd have 2n plus 1 or 2n minus 1. All right, so again, these are some very common things that come up in patterns whenever we're trying to come up with an explicit function for our sequence. Okay, so next question here. Example 8. Whoa, why'd you come up? Okay, I didn't want you to. For what values of r is the sequence r to the n convergent? This is an example of something that is called a geometric sequence. We have some sort of power. It looks exponential, right? We have some sort of this. The reason why it's an r here is because that is what is called the common ratio. Let me demonstrate that real quick for you, okay? So let's say that our r value is just the number 2. Let's say for r is equal to 2, then you would have like this. 2 to the first power is a 2, to the second power to a 4, an 8, a 16, a 32, and so on, right? So if you were trying to determine what the pattern is, one of the things that you look for is what the common ratio between these terms is. So in other words, 4 divided by 2 gives you a 2, so it's been multiplied by 2. 8 divided by 4 also gives you a 2, it's been multiplied by 2, and then so on, right? Times 2, times 2. Whoops, a plus 2. What are you on? What? Okay, times 2. And so really this one is 2 to the nth power. Would that converge? No, obviously this is exponential growth. It's just going to keep getting bigger and bigger and bigger and bigger and bigger. So what if instead I did r equals a half, something like that one? Then you have a half, a fourth, an eighth, a 16th, and 1 over 32 and so on, right? And you can see that these terms are getting smaller and smaller and smaller. So this is identical to the one that we looked at in the previous video. This one is just 1 over 2 to the n, and that one would converge, right? That converges to 0, which is a good thing. And that's what we want, is like, what are the values of r for which this whole entire thing is going to be convergent? Well, we've found one of them, it's a half. What's the difference between these two things? Here you have exponential growth. That happens when your r value is greater than 1. And then over here, when it's less than 1, that's when this thing is exponential decay, and the terms are going to get closer and closer to 0. So now I think we're zeroing in on what are all of the possible values here for r. Okay, so divergent goes like this. Divergence is going to happen when r is greater than 1, because that's going to make exponential growth. Exponential, I think there should be an I in there someplace. Let's just throw one in there right there. Growth. If I can spell growth correctly. Pulled it off. Okay. Yeah, so it's just going to keep getting bigger and bigger and bigger, like this example that I did right here. You're going to be convergent if your r value is less than 1. Well, actually, here, let's amend this. Let's make it between 0 and 1 like this, right? Okay, so that you have some sort of ratio, r values like a half, or it's a fourth, it's 3/4 or something like that, because this one is now exponential decay. So all of the terms are going to get closer and closer to 0. All right, okay then. Notice the number that we left out here is 1. What happens when your R value is 1? Okay, so if I were to plug that into this little formula here, it's 1 to the first power, 1 to the second power, 1 to the third power. It's 1, it's 1, it's 1, it's always 1. Do these terms, do these terms converge to something in particular? Notice that I've got a double comma in here. You know why? It's because I missed a 1. Anyway, Do they converge? Yeah, also, obviously they converge to 1. Right, there you go. Okay, so that one actually is convergent as well. But what about negative numbers? Would that work as well? So what if I did R is equal to a negative 1/2? Something like that. All right, so then you're taking powers of negative 1/2. What happens is that you have, let's see, to the first power, you have negative 1/2. And then if you multiply that by negative 1/2, you get positive 1/4. If you multiply that by negative 1/2, then you get negative 1/8. Do you see what's happening? Positive 1/16, negative 1 over 32. And they alternate. Well, we've already talked about by absolute value theorem, if this one right here converges, positive 1/2, so is the alternating one going to converge, because all we would be doing is taking the absolute value of it. Really what it looks like, what it comes down to is this. You got negative 1/2 to the nth power. So I'm just going to rewrite this. I'm going to rewrite this as negative 1 times 1/2 raised to the nth power. And I have a product raised to the nth power by a property of exponents. That means that is equal to negative 1 to the nth times 1/2 to the nth. And then you can see that we have our alternator that's just right out here. And this technique that I just did here, this is sometimes something that you need to do whenever we're dealing with our sequences and eventually our series. So this means that we can expand this right here to go from, actually, not from 0 to 1. It actually is from negative 1 to 1. Oh, but we didn't actually try 0. Is it obvious if 0 is what your R is? It's going to converge. So let's see. 0 to the first power, 0. 0 to the second power, 0. 0, 0, 0. Yeah, so that one is also going to converge to 0, so that's good. Anything beyond that, like to the left of it, if you had, say, R is equal to a negative 2, then that's, again, it's like a negative 1 to the nth power times 2 to the nth power. You take the absolute value of that, that gets rid of the alternator and just makes that 2 to the nth power, which is not going to converge. Right, that one will diverge. All right, so then let's kind of summarize this right over here. Here's some pictures right here. So this is the first one that we were looking at. R to the n, the limit as n approaches infinity, is going to equal infinity. In other words, diverge if R is greater than 1, and it's going to be equal to 0 in between 0 and 1. That was the first case that we looked at, and then here are some graphs to demonstrate that. Okay, but then here, what happens whenever we have some negative ones in there? Well, anything that's less than negative 1, it's still going to diverge. Anything that is between negative 1 and 0, they're going to oscillate closer and closer to the n-axis right here, the x-axis, whatever, and then also get closer and closer to 0. So they're also convergent. So here's all of that completely summarized. The sequence R to the n, which we're calling a geometric series, is convergent if negative 1 is less than R, which is less than or equal to positive 1, and divergent for all other values. As you can see right here, they actually converge to 0. In between negative 1 and 1, it's going to converge to 1 if R is equal to 1, as we saw before. And notice that on here, it excluded negative 1, and that was not one that we talked about. So let's actually look at that one then. So what if we just have an R value is equal to negative 1? So then we have the terms of our sequence, which go negative 1. I'm going to raise it to the first power, positive 1, then negative 1, then positive 1. and so on. It just alternates. I don't have any terms of the sequence which are kind of making it shrink down or whatever. That's all you get, is that it alternates between being a negative one, a positive one, a negative one, and a positive one. This oscillates, so it's going to diverge.